Hi, this is Glenn Daehn. It looks like I'm recording. It's unfortunate we can't be together live. This is the best we can do for now. I'm honored to give this talk for the Tylen Alton Honorary Symposium. And let me just get right back into it. And I'm hoping to see Tylen and many others be live when we have the discussion. I'll try to keep this brief and hopefully fairly entertaining. This is really a collection of ideas that have been developed by a number of us over some time now. And let me see if this gets to the right mode here. Looks like I am. This is a concept that has come up from a lot of discussions we call hybrid autonomous manufacturing. And you can see the group of people. There's a bunch of people at Ohio State, graduate student I work with, Brian Thurston, and you'll see a lot of his work in this. David Dean, Mike Graver, Stephen Isbode, and Nate Ames are part of the team here. I talked with it quite a bit. And we have alliances with other universities that we've been talking to, and I'll hit that. First of all, this is in the Tylen Alton Honorary Symposium. I've been here at Ohio State, been deeply influenced by Tylen, like I think a lot of other people have. I came here in autumn of '87, and this was at the time the Engineering Research Center for Net Shape Forming was at its peak. And Tylen really immersed me into a lot of very industrially relevant problems and showed a very scientific approach to solving them. And again, tried to bring in all of these things related to process, bringing the material, the machine, and all of that. And he has a great heritage in doing that. And hopefully, I'm providing some ideas that take this a little bit further. So here's kind of the basic idea. What we'd often like to do in any manufacturing process is have agility, shape, and properties. And the promise of additive manufacturing is you don't need these big tools and dies and all of that. The problem with additive manufacturing is you really, as a metallurgist, I see that we have very little control over the microstructure. Basically, structural metallurgy is often called heat and beat metallurgy. And because we can do so much in terms of refining the material structure by deformation processing, thermomechanical processing, fixed dies really limit your agility. The question really is, what can we do without dies? What can we do with the digital manufacturing process? And what might be the steps we need to get there? And that's something that a number of us have been talking informally and formally about for some time now. And I think have some hopefully interesting ideas, interesting to me at least. This follows on three real waves. This is really, I think, the third wave of digital manufacturing. First, we had subtractive manufacturing. And all these things take a long time to develop. Subtractive manufacturing was initially developed in, just after World War II at MIT, still developing today. Additive manufacturing, again, goes a history that precedes even the 1990s into the 1980s. These ideas were being developed, and they're still being developed today. One of the big problems, though, is you really don't have that much in the way of fundamental degrees of freedom you can use to process materials to get optimum structures. That's why forgings are still often our gold standard for high performance materials. And can we get forging-like properties out of a process that's agile? That's kind of a key question in this short talk. I think the answer is yes, we can. And the blacksmith has shown us the way to do that. And the blacksmith basically can change properties and change shape. This is a metamorphosis, just like what do you call it, a caterpillar turns into a butterfly. That's a metamorphosis. It changes shape and properties. We do the same thing with metals. The blacksmith has done this through a combination of actuators, like a hammer, computation, thinking about things, sensors, which are his eyes, robotics, which is basically moving this about. And then I understand back in the day, they might have had dragons to give you the thermal properties, but today we use things like induction lasers and all that. All of these things can be done basically much better than a blacksmith could. So this is kind of where we start. We've published a fair bit of this. One movie I do want to show is something that we came up with is what we call the LIFT Prize. Under the LIFT Manufacturing USA Institute, we offered a prize of $25,000 to somebody who could develop a system that could numerically take plasticine and reshape it just by code into various shapes. We put 3 target shapes out, said, please make 2 of the 3. This was the winning submission that came from Brian Thurston, who have subsequently recruited to work with me. And what you see on the left is forming plasticine to make this bracket shape. And what you see on the right is forming it to make this horseshoe shape. And what you see is by a programmed number of incremental steps, you end up making both of these parts. And again, simply by changing code, you can make other parts. What we would like to have is sort of a G code equivalent for deformation that we would have for subtractive and additive manufacturing. It turns out G code is really the key to both of these, but deformation is more complicated in that the kinematics are more complicated, and then also the effect on materials properties are also somewhat more complicated. And you can see one of the tricks here is you're seeing tool changes that are happening up in the top left, and then you're also going to see a tool change there on the top right, where we have basically penetration tools that are going in. And you can see we get pretty close to the shape in both cases. The technical part of this is actually quite easy for any of us in the metal forming community. We know that volume is conserved, so you squeeze something one way, it'll expand the other directions. And the other key idea here is that if you do things in small increments, take small bites, you need relatively low forces. So you just take lots of small bites rather than one big tool. And if you do things also, if you play with clay as a kid, you know that you squeeze something, you can get that dimension pretty close, get this dimension pretty close. And if you just keep iterating back and forth, you can get pretty much the dimension you want, make a cube out of a sphere, for example. Well, this idea has been around. We got this going. Alan Taub worked with me on this at Lyft. We developed through TMS a report, Metamorphic Manufacturing report that's available online that had about a dozen experts, many of them known to this community that were part of that. And we said, you know, these key ideas are sensors, thermal treatment, actuators, robots, and computation. STARK is the acronym there. We have a mission badge. And then we also came up with, there are things we can learn, insights we can take from things that are well developed, including human blacksmiths, CNC machining, additive manufacturing. And the other thing that's really, really important with this is understanding the state of the material so that you can make parts that somebody's life might depend on. Understand you're inside the right metallurgical regime where you have enough strain, for example, the right temperatures and so forth to get the properties you want. And that's really important. In addition, this wasn't part of the report, but some of the earlier thinking, there are lots and lots of processes that you can use in an incremental way. Sheet forming, we think a lot about single and double point incremental, but there's English wheels, there's stretchers, there's shrinkers. There's things we can do with bars like this. You know, this comes out of Germany, showing incremental deformation, ring rolling, rolling shapes, bending. All these things can be used. These all basically harness incremental small tools. Well, we've kind of gone further with that. Said, boy, if we can start breaking these processes down, isn't there a lot that we can really do incrementally? And again, I think, yes, there is. And fundamental operations we might consider are molding, shaping things, depositing things, removing things, deforming things is also important, which is a little separate from molding. Transformation is very important. This is something that's sometimes underappreciated in, I think, additive manufacturing or transformations we often do under strain. Assembly is also important. And then we have these fundamental tools, all of which we can use in small and incremental ways for heating, deforming, removing, adding, and so forth. And the bigger idea that we've come up with is something that we call hybrid autonomous manufacturing, where you could imagine robots that have a number of tools at their disposal, sensor systems there, and this could act like a robot artisan and make all kinds of stuff. Moreover, a robot can be very reproducible. It can record everything it's done. That gives you a digital thread that you can use for quality assurance. This is sort of a long vision, but we think it's a vision that's worthwhile. If you have that, you could use this at fulfillment centers to make things. You could use this at forward operating bases, for example, to make parts on an aircraft carrier. I'll show you an example where you could use this in an operating room. These agile small systems, you're not going to put a stamping press in space, but you could imagine something like this multi-purposing in space. And also, we believe this is a really good thing for using in STEM education. So these are some of the use cases we think could be quite important with this. They include point of care manufacture, which David Deehn is a colleague. He and I have talked quite a bit, and others. Numerical forgings, again, by taking small bites, you can also imagine making very, very large forgings this way, much bigger than you could make with a given press. Bringing this with wire arc additive manufacturing, we think is kind of a particularly attractive thing to do, in that you can braid composition from place to place, make a preform that's useful, and also there's very high deposition rates available with wire arc additive. Last thing I'll show you some progress that Brian Thurston has made in a little bit with something we call PETFABs, Physical Exploration and Training Factory Automaton Box. It's kind of a fancy acronym, but this is something that I think you can use to validate the process and also use this as a place to teach career technical education and STEM skills. We think this is the first of a long march towards autonomy. In automotive engineering, they have 5 levels of autonomy going from 0 to 5. I'll let you study that on your own. But we think there's something very similar going on with manufacturing autonomy, where you can go from no automation. CNC machining is level 1. If you put closed loop control on that to zero out errors, that's level 2. Level 3 is if you start coupling that with simulations to actually make sure that you're driving materials properties in the right way, that would be level 3. Level 4 is where things really start to get interesting, where you can imagine the systems themselves can transfer things from one process to another, from a welding process to a deformation process, maybe to a final machining process. All of that is done without human intervention, and that could be done either with the part moving or things coming to the material. And then we think the highest level would be that artificial intelligence system talks with you, basically understands the trade-offs, understands that some materials might take longer, be more expensive, and develops things that way. Turns out there are actually a lot of companies going in this direction, mashing up artificial intelligence with all of these things. There are examples in welding plus AI, Path Robotics here in Columbus. Machining plus AI and automated transfers is being done by a company called Form Logic. Deformation plus artificial intelligence is being done by Machina Labs. Assembly and AI is being done by rival vehicles, and then design is being done by basically all the CAD companies. So we think this is something that's already happening, and this deformation community should hop on board. Last thing I want to show is some progress we're making with Brian Thurston. This is something we planned on doing with real metal, but when COVID hit, we moved it to plasticine and in his apartment, and I think he's made some very nice progress there. They'll show you. Basically, what he's been doing is taking a system. He, by the way, is the person that one of the team that won the Lift Prize. He's now continuing his work with plasticine, and now he's got a small arbor press and continuing with plasticine. And the idea is to take something and make a target shape out of it with a progression of automated steps, and do that in a way that where you could put in code to do pretty much any other thing that you'd like. This is a demonstration of that algorithm that I will show here, and I will skip over some of it in deference to time. Let's see if it is moving now. So anyway, this is code that he's written. This is a graphic display of what's going on. This is based on a real scan. This is, in this case, now the target model that's gone in here. What he's basically doing is, this is really a digital twin of this operation. On the right, you see simulation of what's going on, and he's using lightweight gaming code basically to do this, rather than full-on finite element and so forth that we might use in academics. And now what you see is, this is the part, this is the shape that he is moving towards. And now what you see is basically 2 steps, where what he's doing is going to take basically the major diameter down. In this case, there's actually excess material there. And then there will be a second operation that forms these desired flutes. And I'm going to move this on just a little bit for time. And now we're going to form to the target model. And he's starting to put these flutes in that case. And again, you see the digital twin on the right. The beauty of using something like gaming code is this can be done at the same kind of kind of response rate that an operation is being done. It's not an offline simulation, but you could take that gaming code and do further simulations with it to make sure you have the right strain distributions and other characteristics. And that's basically where we'd like to take this over in the long run. Let's get towards the end and kind of show what this thing looks like. And here's the final result. You can see it looks quite a bit like the initial one, and there's also been a bit of a truncation thing that was done there. Got rid of some excess material. So we are on track. Among the next steps we will be doing with this is doing this with real metal. Here at Ohio State, we're fortunate to have the Center for Design and Manufacturing Excellence, which has its Artificially Intelligent Manufacturing Systems Lab. And in that, we have multiple vision systems. We have multiple robots, and we have a small press, which is now numerically controlled. And we will be starting to run these kinds of operations. And I should also mention there's welding equipment and machining equipment in this lab, and we can start to visualize and approach this vision of hybrid autonomous manufacturing. So I will end there. I'd be more than happy to engage in discussion of multiple types. Thank you, and it's unfortunate we can't be together live.